Hi guys. Um, Welcome to what might be our last lesson for this unit. This is it's word problems, but it's like a very particular kind of word problem, which many students find to be difficult, but if we use our distance equals rate times time table to do these, it makes it a little bit easier. Just to remind you, it's like distance equals rate times time, and we do like a little table where we put the distance in one box and the rate in another and the time in another, and it just kind of helps organize the information. And there's usually either two trips. We saw that for the problems that were like about rates with like a plane in the air, like a plane with wind and a plane into the wind and a plane against the wind, the whole headwind tailwind thing. There's one of those at the end of this lesson too, but these are a little bit different and they're kind of like generic stereotypical problems. So let's just dive into it. So you basically have these two trains and they're going from Boston to DC. And usually the train doesn't get to DC. So the first train leaves at noon. That's important. And it goes this direction and its speed is 60. And it goes for some X number of hours or minutes or whatever. Again, these are very generic, typical kinds of problems. And then 2 hours after it leaves, another train leaves, going the same direction on like a parallel track. That means they're not going to run into each other. And it leaves, but it's going 90 kilometers per hour. And at some point, since this second train is going faster than the first one, it's going to catch up to the first one. And the question is, what time does that happen? So there's a couple ways to do this. But I'm going to give you the table way, and maybe I'll tell you about the other way at the end, or we can talk about it in class or something. There's more than one way to do these, but let's just do the table. So our table is going to be distance, rate, and time. Distance, rate, and time. Distance, rate, and time. And let's say we got the Vermont Railways. That's going to be this one. We'll call that VR. And then the Amtrak Metroliner, we'll call that AM. And so this is going to be the distance, rate, and time for the Vermont one and the distance, rate, and time for the Amtrak. So one thing I know I can fill in here, I know the Vermont Railways train goes 60, so I can put that in the rate. I know that the Amtrak Metroliner goes 90. So we have these two rates, but like we don't have distances or times. And this part, the catch up to the freight train part, tells me like this one's going to go some distance, and at some point they're going to have gone the same distance. And that's what it means to catch up. It means that whatever distance the first train has gone, the second train has gone the same distance because they start at the same place, so they catch up when they've gone the same distance. So I don't know what that is, but I can just call it D. Each train has gone some distance. I don't know what it is, but I'm just going to call it D. Maybe it's 100 kilometers. Maybe it's 300 kilometers. I don't know, but it's the same for both trains because that's what it means for one train to catch up with the other one. And now the time is a little tricky. So it takes, I don't know what this is, but I know that the time for the Vermont train, because it left 2 hours earlier, has traveled 2 hours longer than this train has, because this one was going for 2 hours before this one even left. So I could say, let's imagine I call this time T. I know that this train has gone has been traveling for 2 less hours because it says this one left 2 hours later. It's actually at 2 o'clock because this one left at noon, but it doesn't really matter as long as it's 2 hours later. Whatever the time that this train has been traveling for when they catch up to each other, this train's been traveling for 2 hours less. So I can write that as T minus 2. That's an important idea here. 2 hours later means 2 hours less time spent traveling. So I have a distance, which is the same. I have the rates, which I was given, and then I had to kind of come up with the t and the t minus 2 based on the fact that this one left 2 hours later. And this leads me to two equations. Distance equals rate times time. Distance equals rate times time. So d equals 60t. Let's write that a little higher so we can see that it came from this top line of the table gives me d equals 60t. The bottom line gives me d equals 90 times t minus 2. And so now, again, there's two ways. This is now a system of equations, system of two equations with two variables. There are three ways to solve it: graphing, substitution, and elimination. This is one of those times where it's good to be okay with doing any of the three ways. The one we're for sure not going to do is graph, but because this says d equals something and this says d equals something, the easiest way to do this is substitution. Instead of writing d down here, because d is equal to 60t, I can replace this with 60t. I can say 60t equals 90 times t minus 2. And now I have an equation with just one variable, which is relatively easy to solve. I would distribute the 90 into the parentheses, so I get 90t minus 180. Subtract the 90t from both sides. So I do minus 90t on both sides. I get 60t minus 90t is negative 30t. And this side is just left with negative 180. If I divide both sides by 30, I get t equals 6. So this is an answer, but the question specifically asks, at what time will the Metroliner catch up? And like, I got to remember what t actually represented, which was the number of hours this first train traveled. We said it left at some time and it traveled for t hours. Well, if t is 6, that means it traveled at some time. Sorry, it left at some time and traveled for 6 hours. And the time that it left was noon. So the answer to this question, t equals 6, implies that they caught up, that the trains were at the same distance at 6 p.m. because that is 6 hours after noon. So for these train problems, not always a train, it could be boats or cars or whatever, but when you have two things moving at different speeds, it's usually a good idea to set up one of these tables. So you can figure out like what you want the distance to be. You can figure out it just helps you organize the information. To me, the trickiest part of this is the t and the t minus 2, to realize that 2 hours later means that this second train traveled for 2 hours less time than this one did. And then you set up your equations, you solve. Doing either method would work, but I think substitution was easier here. And then you get an answer, and then this is important to reframe it in the context of the problem. Actually understand what t equals 6 means, 6 p.m. So that's one problem. This is like I said, a pretty typical algebra question about the two trains. I put this one in here because it's a little bit different. These ones are a little bit different. So see if I can do this with the table. I probably wouldn't normally do this with a table, but you can do it with a table probably. D equals R times T. And I have these two cars. Doesn't really care. I'll say one car. We'll call that car 1. And the other, I'll call car 2. So I have these two different cars. So they leave Salt Lake City traveling opposite directions. One car travels at the speed of 80, so I can put that here in my rate. And the other car at 96. And then in how many hours will they be 528 kilometers apart? This time I can look and I can be like, well, since they left traveling in opposite directions, if they don't tell me that it's a different time, you have to assume that they left at the same time. So however long the first car travels for, the second car travels for the same time, and we want to know at what point are they 528 kilometers apart. It kind of looks like this. the picture. We got an 80 and a 96. So going opposite directions. And like, the question is, when this is 528, what is t? So the t is going to be the same for both cars because they travel for the same amount of time. The distance here is where it gets a little tricky. But we can do this. We know that the total distance, we want whatever d is for car 1 and the d for car 2, we want them to add up to 528. And there's a kind of a trick here, which is this. If this car travels for d kilometers, this car travels for 528 minus d kilometers. And there's two ways to think about why that's true. One is this. If I have this little setup here, and like, let's say this is 528. This is now the situation which they want the answer for when this is 528 kilometers. Let's say car 1, which is the 80 kilometer per hour car, travels for d kilometers. And like, the question is, what do I add here? What does this equal when this whole thing is 528? And the answer is, well, let's say if this guy traveled for 28 kilometers, then this would have to be 500. That was kind of an easy one because you can just look and see 528 minus 28 is 500. But let's say this d was 200. Well, what do I add to 200 to get to 528? I add 328. And if you think about the operations that I'm doing to get these answers, this is really a subtraction problem. What do I add to something to get something else is a subtraction problem. So the answer is whatever d was, I take 528 and I subtract d from it. Basically, if this whole thing is 528 and this is d, this is whatever's left over when you take d away from 28, which is what 528 minus d is. And if you think about these two distances here, if you add these two distances together, d plus 528 minus d, that equals, because the d's cancel out, it always equals 528, which is what I was hoping was going to happen. So whenever you have like a total distance and you call one of them x or d or whatever, the other one's the total distance minus x or d or whatever. So this gives me my two equations. D equals 80t and 500, this is d equals 80 times t, and then I get 528 minus d equals 96t. And you could substitute this d equals 80t in right here and get 528 minus 80t. That's a fine way to do it. Maybe I'll add these two equations together because I can see right away that this is a one positive d and this is a negative d. So I add them together, I get 528 equals, I think that's 176t. I divide both sides by 176. That leaves me t equals, is that 3 maybe? Got to break out the old calculator to do that one. 528 divided by 176 is 3. So t is 3, and this time there's no time like 12 o'clock or 1 o'clock when they left. So the answer is just, it says in how many hours? 3 hours. That's the answer. So this one you can do with the table. There's another way to do it. We can talk about that later, but I just kind of want to be consistent and show you guys just one way to do these. And to me, the big trick here was the d and the 528 minus d. Like, to see that these things add up to the whole distance is the important concept to get here. There's a lot of ways these questions can be asked. I want to give you a couple of different strategies in case it's not always the same thing. Let's see what else we got here. This one, and this one, this one. This one's pretty tricky, the old point of no return problem. So I'm going to break this video and I'll do the next one's the next video.